Hello, this is Mr. Sorrentino again, and this is another video from the Math 31 course. And this one is dealing with section 5.5, solving exponential equations and logarithmic equations. This is where we're going to start making use of some of those logarithmic properties we learned in the previous lesson, as well as some exponent rules you learned in the past. And essentially, another skill that we're going to be making use of is the fact that I can rewrite a logarithmic statement or an exponential statement into an equivalent logarithmic statement. Because generally that's what I do if I'm encountered with an equation that's exponential and I don't know offhand what the number is going to be, unless I see a perfect, if I say like, three, if I see like something like 3 to the x power equals 9, then I say, well, I know that 3 squared equals 9, so, you know, that's easy, x equals 2. But if I start saying, okay, well, 3 to the x power equals 17, I run into a difficulty there. And basically to solve that, I should rewrite that as the equivalent logarithm and then go from there. Likewise with a logarithm, if I rewrite it as an exponential statement, it might make more sense, and I'll be able to figure out what's going on with it just by plugging it into my calculator or, knowing my powers well. Um, but there's going to be complications as we move along with this, and as we go through these examples, hopefully you'll see how some of these complications need to be handled so that you can start practicing and handling them yourself. There's another key point that they bring up here, and it's just most students figure this part out on their own, but it's good. It's worth saying. If I have the same base raised to what is represented as two different powers, if I have two different variables of this and I say they're equal to each other, that means, well, those exponents have to be equal to each other. So that stands to reason. And if I do a log of the same base, the two things, and they're equal to each other, but I have two different variables represented, that means those two things have to equal each other as well. So, and this premise for the logarithm in particular is becoming very important because notice that, I can drop those logarithms as long as I have a single logarithmic statement on the left and a single logarithmic statement on the right. And I can rewrite a logarithmic statement as an exponential statement as long as I have a single logarithmic statement that I'm doing that for. When I start having multiple logarithm statements together, being added or subtracted or things like that, that's where things go awry, and I have to start using some of those properties as we move along. And one last thing, because a to the exponentials functions like a to the x have a domain restriction, and because as a result the log base a of y would have a range restriction, um, because of those restrictions, I have certain things, certain values that won't work with these. And if I have values that won't work with them, when I start solving these equations, I have the potential for extraneous solutions because for me to solve these, I have to work under the assumption that what I'm producing, what this equation, both sides exist for me to do this. And so, especially the logarithmic equations, as they get more complicated, they're fraught full of potential extraneous solutions. That doesn't mean there's going to be one. It just means that you need to make sure you're looking and checking to make sure that one or both of the answers you produce are not extraneous. Because the moment you don't do that is going to be the moment that you have a problem that there is an extraneous solution. You're going to tell me there's two answers when one of them, in fact, is not an answer. So be careful about that. So let's move on to the first example. These first ones are not extraordinarily difficult. A is pretty easy. B, not too much more difficult as long as you rewrite it correctly. Um, and when we get to C, a little bit more problematic, but you'll see in the end, not too bad. So 2 to the x power equals 8. This one is almost a no-brainer because most people do know their powers of 2. If you can sit here and say, okay, well, I know that 8 is 2 times 2 times 2, which is 2 cubed. Well, 2 to the x equals 2 cubed, and as mentioned above, if I have the same base and two different representations of the exponent, then those two things have to be equal to each other. So x equals 3 is the answer. That one's pretty straightforward. When I do the log base 5 of x equaling 3, well, as it looks right here, it's like, well, what number should I be putting in there? If you state it right, you say, okay, what number is equal to, gives me an exponent of 3 when I look at it as being a power of 5. That still might be a little bit difficult to put it in that kind of mannerism. So let's rewrite this as an exponential. So it's an equivalent exponential. This is going to be 5 to the third power equals x. And so x is going to be 5 times 5 times 5, which is 125. So again, pretty straightforward, not very difficult. All I had to do was rewrite that as an exponential equation, and I had my x alone on one side, and I had a number raised to another number power, and that's pretty straightforward. Just either think about what it means or just throw it into your calculator, you got it. Part C, not much more difficult. Now again, you have to make sure that you're at least following some basic equation solving techniques. Obviously, I want to get x alone on one side of the equation. I have a subtraction of 2 attached to it. I also have a logarithm base 7 attached to that quantity of x minus 2. Now, the log base 7 of the quantity of x minus 2 is more or less attached to those parentheses. Those parentheses are not going to go, the need for those parentheses is not going to go away, and therefore I just can't skip writing the parentheses until that logarithm is gone. And basically that minus 2 can't go away until the parentheses go away. So that lets me know what I need to take care of first in this instance. In this instance, that logarithm base 7 has to go. So what I have to do is say, okay, well, according to my rules that I have for this, I'm going to rewrite this as an exponential statement. So my exponential base will be 7. This is going to be the exponent, 7 to the first, equals x minus 2, which is basically the same thing as saying x minus 2 equals 7. And then, of course, it's a very simplistic equation at this point. I'm going to add 2 to both sides, and I get that x equals 9. And if you look back on it and say, well, for me to get a 1 on that side, if you know more about the logarithms, well, then 7 to the first power has to be what is on that side there, and that's what x minus 2 has to equal. So you can rewrite it as the exponential, get to the same point, whatever. So these are pretty straightforward, and it's somewhat easy. The easier ones, don't really have much chance of having extraneous solutions, but you should always be aware that you should double check. Log base 7 of 9 minus 2, well, 9 minus 2 is 7, or 7 to the first. The log base 7 of 7 to the first is 7, or 1, so it does work. So it's not extraneous. As we get into more complex ones, like example 2, then you have to start looking a little bit more closely. Now, exponential equations don't tend to have as much of a chance of having extraneous solutions as the logarithmic ones. It's still worth your time to check them and make sure that they work. So let's head on to example 2. There we go. Now 3 to the 3x power equals 50. So again, it wouldn't be too bad if 50 was a power of 3. It isn't. I mean, I have my 3 to the 7th, my 3 to the third power, which is 27, and I have my 3 to the fourth power, which is 81. Those, whatever 3x is going to be, it's probably going to be some sort of irrational number. And, that's going to make it a little bit more difficult. It's going to be an irrational number that's between, 3 and 4. But, other than that, I don't have a specific knowledge of what that is unless I have to resort to using the calculator. So I am going to rewrite this as an equivalent logarithmic statement. So I'm going to have the log base 3 of 50 equaling 3x. How you want to handle it after this point is up to you, but make sure you're communicating what it is you're doing. If you have the ability to do a log base 3 of 50 on your calculator, by all means, just you can get the evaluation of that and say, okay, well, I would just divide both sides by 3 at that point and say, okay, there you go. However, if you don't have access to that or know how to get to that point on your calculator, or if your calculator doesn't even have it, to go further with this, I'd probably have to use the change of base formula to say, okay, that's going to be log base 10 of 50 over log base 10 of 3. And to get x alone, of course, I'm going to divide both sides by 3, which is the same thing as multiplying by 1/3. So I'm going to have the log of 50 divided by 3 times the log of 3. At this point, you can put it into your calculator. Make sure that you are putting it in correctly. Again, if you have a newer TI-84 calculator that has the newest operating system, you can actually have a fraction bar command where you can clearly put what's on top and what's on bottom separate. If you're writing from left to right, please make sure as you do this that you're putting it into your calculator. If you're just going into your basic window and you're dividing by the quantity of 3 times the log of 3, because that multiplication is occurring specifically before that division occurs. So it isn't just like, you could just say divide and multiply using the order of operations. So it's going to divide by 3 and then multiply that whole answer by the log of 3, whereas you want the log of 3 being part of the division. So if I carry through this, I get that x is approximately 1.1870. And again, to do a check on this, again with your calculator, do 3 to the 3 times 1.187 power. When I do that on my calculator, I get about 50.0067. So that's good enough. That kind of checks out for me that works, and I got a correct answer for this. And on the final exam, you might be given problems like this, and you'll be asked to more or less stop here. To give me a statement written in logarithms that would produce the correct answer, that is the statement that would do that. Because you won't have the calculator, so make sure you know how to set this up accordingly as if you don't have the calculator. B, a little bit more difficult because I have an exponential on the left, I have an exponential on the right, and unfortunately they're not the same bases. If they're not the same bases, it's probably just best to interject a logarithm. Someone said, well, should I use log base 5 or log base 3? And you could use either one of those, and that'd be fine. It's going to work really well on one side of the equation, not so well on the other. And on the side it doesn't work that well with, you might have to use a change of base formula anyway. The one nice thing about exponential equations, for me to solve them, I do ultimately have to use a logarithm, but I don't have to use any particular logarithm, as long as it's any logarithm. And so one way of handling it, when you have a situation like this where you have, an exponential equal to an exponential and they're different bases, the best thing to do is just rewrite that, of doing the log of both sides. These have to be equal to each other because, the two quantities themselves are equal to each other, so their logarithm should be equal. The reason why it's good to write it that way is because now I have these exponents the issue with solving the equations that are exponential is getting those x's, or whatever the variable might be, out of the exponent and being written as bases. The only rule we have that helps us do that is the power property, which says that I can now rewrite this as x minus 1 times the log of 5 equals 2x times the log of 3. Where students have some difficulty with this is, they want to start evaluating and say, okay, the log of 5 is this, the log of 3 is this, put an approximation in. We're still awfully early in this solution process. If I'm putting numbers in and already rounding into 4 decimal places, then if I have a couple more steps to go, the next step I'm going to have some more stuff that needs to be done, and I'm going to be rounding yet again to 4 decimal places. And then the next step I'm going to be doing some more computations and again be rounding to 4 decimal places. And what sometimes happens in those instances is that whatever value of x I get, when I start trying to check to see if I get the same quantity, if I put that x into 5 to the x minus 1 power versus 3 to the 2x power, I end up seeing that the two answers look different enough to warrant confusion, mostly because of rounding errors and doing a little bit too much rounding along the way. So what I suggest doing, and it does take some practice for students to get in the hang of doing this, the log of 5 is a number. The log of 3 is a number. Just treat these as being numbers for the time being. I want to get x alone, but right now, for me to get x alone, I do have to manipulate a few things and do some operations to make that happen. If I treat these as numbers, then I'm going to have x times the log of 5 minus the log of 5 equaling, well, this one doesn't have much to do with this, 2x times the log of 3. I want to get all my x's on one side, and anything, this is log of 5, not log base 5. Make sure you're showing the difference between them. I'm going to get my x's all on one side, and anything that doesn't have an x attached to it on the other side. I like having my variables on the left, so I would subtract 2x log 3 from both sides. And I would also add log 5 to both sides. And so what happens with those is that, I got a cancellation here, I have a cancellation here. So I have x times the log of 5 minus 2x times the log of 3 equaling the log of 5. Without me figuring out what log 5 is and log 3 is, I kind of lose my ability just to combine some like terms, because if I just had some number times x, and I actually wrote what the number is, and then some number times x times this 2 out here, I'd be able to carry through the subtraction and combine those like terms. Well, since I'm doing it this way to keep this being as exact as possible, I kind of lose my ability to do that. But what I can do is I can factor out the x. And if I do that, I'm going to be left with x times the quantity log of 5 minus 2 times the log of 3 equaling the log of 5. And of course, this one here could be simplified a bit more by moving that 2 to the inside, and I would have x times the log of 5 minus the log of 3 squared, which would just be 9, equaling the log of 5. Since these both are numbers now, me subtracting them would produce yet another number. And so I do have x times a number equaling a number. So from a basic equation standpoint, all I really need to do now is just divide both sides by the log of 5 minus the log of 9. And scooching this down a little bit, that would leave me with x equaling the log of 5 over the log of 5 minus the log of 9. Please don't do any cancellation saying, well, I have a log 5 on top and a log 5 on bottom. This term here has no log 5s in them. You would not be able to cancel them. The other thing you would be able to do at this point is approximate this and say, okay, well, that's going to be log 5 divided by log 5 minus log 9. And you get about negative 2.7381. Which, if you were rounding, if you like here follow that and then start rounding this step, this step, this step, you'd have 3 different steps along the way where you could potentially be computing and doing yet more rounding, and it may not become quite this answer. It might be like negative 2.7408 or something like that. I mean, it seems it's pretty close, but not exactly the same thing. And if you put it into the above there, those two things won't look very close to being equal to each other. Meanwhile, if you put these in, on the left-hand side, if I put this number in, the left-hand side, I'm going to have 5 to the negative 3.7381, which is 0.002439. If I put it into this one over here, I get 0.002439. You know, when I'm rounding them off. So I mean, with keeping the decimal places and not rounding throughout this entire problem makes it more likely that the answer I plug it in, if it's intended to be the answer, it's going to produce the results I'm expecting. Sometimes students, especially when you're looking for situations where you could have extraneous solutions, you don't want to have a big discrepancy between answers due to rounding errors, and then you end up saying, well, they're not the same thing, and you throw one out and say it's an extraneous solution, and meanwhile it isn't. So keep that in mind and watch the rounding is basically the moral of that story. The next one's a little bit more problematic because it's not just an exponential equation. And notice I do have exponentials, and they're base E at that. I'm going to have to do some work on this one. Now, throughout the course, and some of the homework problems that hopefully we've discussed in class, it's always rough when you make these videos before you start a class. It's hard to tell what the conversations were like, you know, but typically in this class I do have conversations where we have situations that have a quadratic structure to them. And this certainly does have some of that going on here. It's going to have a quadratic structure to it eventually, and we're going to have to handle that. And when I start taking functions that are exponential and start putting quadratic things into it, it gets, again, you have the possibility for some extraneous solutions along the way too. So we have to be on the mindful of that. But first of all, let me give you a chance to give this a whirl. See if you can maybe come up with an answer for x, and then I'll show you how to go about doing it. Well, right now what we have here, and I'm going to rewrite this ever so slightly, I have e to the x power minus 24 over e to the x equals a negative 2. Certainly having an e to the x power makes things complicated enough. Having an e to the x power also in the denominator, which gives it some rational feel, not a good thing either. Makes it a little more complicated. Along with that, for me to convert an exponential equation into a logarithmic equation, I just have to have the format, you know, in this case I'd have to have e to some power equals whatever's on this side here. They could have multiple things going on. I could just have a number. I don't have that structure here. I have two exponential statements being added or subtracted together. I have to figure out a way to get to a point where I have something that looks more along the line of that at some point. So I have to play around with this a little bit. And the first thing I'm going to do on both sides of the equation, or to the whole equation for them, is just I'm going to multiply everything by e to the x. The reason being is I want to get rid of this denominator of e to the x. So here again is something we're starting to do operations on this equation, and I'm working under the assumption that everything here exists. Well, 24 over e to the x power could potentially, being that having some rationalness to it, could potentially have extraneous solutions because of the fact that I'm making an assumption that could not exist. In the long run, e to the x power is not going to produce a zero because e is a positive number, and I can't raise a positive number to an exponent and get anything that's zero. So I can get close, but I'm not going to get zero. So probably at this point, me doing this is not going to create the possibility for extraneous solutions, but some other circumstances it might. So keep aware of the fact that when you have to make an assumption that everything exists and everything's fine, in order to keep going on with the equation, that's where you have the potential for extraneous solutions. And so e to the x times e to the x is e to the x plus x, which would just be 2x. Of course, this becomes just a minus 24, and this I'm going to have negative 2 e to the x. I'm going to add 2e to the x to both sides. And so when I do that, I have e to the 2x minus 2e to the x minus 24 equaling 0. So the question a lot of students start asking is, why did I put it into this format? Well, the reason being is that although it's an exponential equation, it has exponential in it, and I'm trying to solve for an exponential base. It also has a quadratic structure to it, in that because this e to the 2x is the same thing as e to the x squared minus 2 e to the x. I'm just going to put parentheses around it to emphasize them. I have something with involving the variable squared minus 2 times something involving the variable that's not being squared minus. This is basically a quadratic format. It has a quadratic structure to it. And so for me to solve this, I can just go with a step and say, okay, well, I'm just going to and I can pick any letter of the alphabet I want. For the sake of argument, I'm just going to pick A to equal e to the x. Recognizing that, I'm going to turn this equation into something with a variable a, but ultimately I am looking for what x is. I need to keep that in mind because of the fact that students will sometimes do with a problem like this is that they'll now solve for a. They'll get that a equals this or a equals that, and they say, okay, I'm done. Well, you're not. You're not done. So, but I'm going to rewrite this now as a squared minus 2a minus 24 equals 0. And whether you use, I'm going to use factoring, but if you use the quadratic formula or what have you, the solution for this isn't too bad, because this would factor into a minus 6 and a plus 4, which means that a minus 6 equals 0 or a plus 4 equals 0, getting back to that zero product principle. And so a would be 6 or a would equal negative 4. But again, I got answers for a, and I'll have students that will say at this point, well, a is 6 or a is negative 4, and that's the answer. Is yay, we're done. It's not. I mean, because first of all, we're not looking for a, we're looking for x. A was something we put into the problem to help us be able to do some work with it, but it's not the answer. So I got to get the x back, and so I'm just going to go back and use this again and say, well, a is e to the x, so e to the x equals 6, or e to the x equals negative 4, which the second one I could automatically right now eliminate. e is a positive number. I cannot raise it to an exponent and get a negative. If you didn't see it there, the next step we would do is turn this into a logarithmic statement. And this one here would be x equals the natural log of 6. This one would be here that x equals the natural log of negative 4. And again, we can't do that one either, because we can't take the natural log of negative 4. So this is the one and only answer here. And so I could say that x equals the natural log of 6, which of course, at this point I could approximate it and just do the natural log of 6 on my calculator, and I have 1.7918 approximately. And if you put that into the original problem, which you should to double check it to make sure it works, and this one does, you will get that the left-hand side with x being 1.7918 is pretty close to negative 2. Again, it's going to be pretty close because I'm only using 4 decimal places. If I use all the decimal places the calculator gave me, and I use my storage functions on my calculator properly, it would come out to be negative 2 exactly. But if I use the 4 decimal places, if I put this 4 decimal version in up here for the x's, this left-hand side becomes 2.000405309 is what my calculator gives me. That's pretty close. I'm not going to have any questions about that. Again, if I was rounding off too much, or if I rounded off anywhere along the way with this, which really isn't many opportunities to do that, you would end up with a totally different answer. An answer that would be maybe different enough to make you wonder, okay, is this close? Is this what the answer is supposed to be, or is this extraneous? And since you do have situations where you have extraneous solutions, if your rounding errors are making your answers be off enough for you to think about possibly eliminating it as an answer, that could cause an issue along the way and end up saying something's extraneous when it isn't. So on to the last one from example 2. And, the equations I tend to give you on tests don't really get this complicated, but they do throw a few of these at you that's the suggested problems from the syllabus, and I think I might have left 1 or 2 of these in the homework that you have to do. But again, with this one, I have 4 to the x minus 4 to the negative x over 4 to the x plus 4 to the negative x equaling 1/4. There's a lot of exponentials going on here. They're all base 4, which is nice, which means eventually I should be able to get this down to something where I could apply the logarithm properly and get an answer. But especially if I rewrite it like this, which is what essentially it's the same thing. It's like saying 4 to the x minus 1 over 4 to the x over 4 to the x plus 1 over 4 to the x equals 1/4. That's just even uglier, but that's what the negative x powers mean. So now I have fractions with fractions in them. The reason why I wrote it that way is because it makes it a little bit more clear about one way I could possibly solve this, and that is simply to multiply the top and bottom of this by 4 to the x. I don't have to multiply both sides by 4 to the x. I don't have to do anything to the right hand side like I had to do a little bit in the previous problem. But here multiplying by 4 to the x over 4 to the x is like multiplying by 1, so I'm not really changing the left hand side. I'm just making it a little bit easier to deal with, because what I end up having here as a result of that is I'm going to have now 4 to the x times 4 to the x is going to give me 4 to the 2x minus 1 over 4 to the 2x plus 1. So it's already looking a little better. Now, knowing that I have basically these as quantities, I have a single fraction on the left and I have a single fraction on the right, I can cross multiply. So 4 to the 2x minus 1 times 4 is going to give me 4 times 4 to the 2x minus 1, and 1 times 4 to the 2x plus 1 is going to give me this over here. in order for me to start manipulating things around, I'm going to have to get rid of the parentheses on the left, which means that I'm going to more than likely have to distribute this. So for me to distribute that, for the 4, I mean, I have basically 4 to the 1 here. 4 to the 1 times 4 to the 2x, I would add the exponents. And so I'm going to have 4 to the 2x plus 1 minus 4 equals 4 to the 2x plus 1. If I add 4 to both sides and subtract away the 4 to the 2x from both sides, that would cause some cancellations here, this and this obviously. So I'm going to have 4 to the 2x plus 1 minus 4 to the 2x. Over here I'm going to have 5. The difficulty that we're having with this is that I have to figure out a way of getting this down to, a single exponential statement so I could eventually make this a logarithmic one. I can't turn what I have now into a logarithmic statement. I have multiple exponential statements on one side of this equation. I can't rewrite it. I don't have that structure yet. And here, looking at the work in hindsight being 2020, might not, for this bottom one down here, when I did this multiplication here, it might have been better just to write it as, instead of having the 4 to the 2x plus 1, leaving it as 4 times 4 to the 2x, and this leaving that as 4 times 4 to the 2x. Because what I can do with this now is that, I have two terms of the 4 to the 2x being multiplied to it. Here's times a 1. And so I could do some factoring. I could factor out a 4 to the 2x, leaving me with a 4 here and a minus 1 here. Make myself a little bit more room. And so basically I have 3 times 4 to the 2x equals 5, which 4 to the 2x would equal a 5/3. Certainly looking a lot simpler now. So we're making progress. And now I do have a single exponential statement on the left-hand side equaling a number. So now I can rewrite this as an equivalent logarithmic statement, where I would say the log base 4 of 5/3 equals 2x, which means that x would equal the log base 4 of 5/3 all divided by 2. That would be a suitable full-blown answer. And again, if you have a calculator that could do the log base 4 of 5/3, if you took this number and did log base 4 of 5/3 divided by 2 and put that value in for all the x's you saw in the original equation, it would work. Without a calculator that does that, though, you might have to break this down further to get a suitable answer with this. You could use properties and whatnot. I'm just going to use the change of base formula. I'm going to have x equals the log of 5/3 over the log of 4 all over 2. Of course, having this being divided by 2, that would just put a multiplication in the denominator. I can rewrite this as the log of 5 minus the log of 3. And this could be rewritten as the log of 16. Still written with logarithmic statements, but not quite as yucky. And something you could certainly put into your calculator and get a more suitable answer. And that comes out to be about 0.1842. And again, if you put that number into your if you put that particular number into your calculator, you would get, if you put this number, as written into this left-hand side, that left-hand side would be written as about 0.249946, which is about equal to 0.25, which is what 1/4 is. I mean, so again, watch the rounding on this with the logarithms, and it's better to, it's better to at least somewhere along the way have some sort of logarithmic statement written, so I know that you came up with the exact right answer before you did any approximations. Um, you know, if you make a mistake in any of the subsequent work, I might take a point off for that, but I usually try to be as lenient on that as long as you had the original answer, that was the original exact correct answer written somewhere along the way. So, those are some of the pitfalls with exponential equations. Let's go look at now example 3, where we deal with some more with logarithmic equations. As I mentioned before, since logarithms have domain restrictions, here's where I run into more potential for extraneous solutions, because when I do the steps necessary to solve a logarithmic equation, I'm working under the assumption that the logarithm or logarithms that I'm trying to perform on the left-hand side, or whatever side of the equation they may be on, can actually exist and work, and they actually do produce something. And so when I look at log base 7 of x squared minus 2, there are some x values that would give me negatives or 0 in that quantity. And those I would not be able to do a log base 7 of. So that means that when I start carrying through other work here, I have to keep in mind for this that x squared minus 2 has to be greater than 0, which means that x squared has to be greater than 2, which means either x has to be less than negative 1.412, whatever it is, 414 or something, or x has to be greater than positive 1.414. And this is approximately what the square root of 2 equals. So I have to keep that in mind. I didn't go through all the inequality steps about how to determine it was an or statement, and what the two parts were. You should know how to do that by now, because we've gone over that in other earlier parts of the course. But keeping that in mind, because if I get any answers that fall outside of this range of values, then I know that they're probably going to be extraneous. I need to throw them out. Not to say I'm going to necessarily have any, but again, I have to keep track and make sure that if they do, they take care of that. So I'd have the log base 7 of something equaling 1. I do have a single logarithmic statement on the left, so I can rewrite this as an exponential. So I can say 7 to the first power equals x squared minus 2. I could add 2 to both sides. X squared would equal 9, which means x would equal a plus or minus 3 when I take the square root of both sides. And I'll show that, or the plus or minus to come here. Now, don't automatically think that because something's negative, and I'm dealing with logarithms, that it cannot be an answer. I should plug both of these in. If I put the log base 7 of 3 squared minus 2, that's the log base 7 of 9 minus 2, which is 7, that equals 1. It works out. If I do the same thing with the negative 3, well, negative 3 squared also produces a positive 9. Positive 9 minus 2 is still 7, and I get the same conclusion. So both of these work, and they're both the solution. So this one did not have any extraneous solutions. That can happen. For B, now if B, let me me scooch this over. If b had been the ln of, something equaling the ln of 3, I could just simply say, okay, get rid of those and say whatever's over here equals 3. That's if I only had a single logarithmic statement on the left and a single logarithmic statement on the right. I don't have that. I have 2 logarithmic statements on the left and 1 on the right, which means that for me to do this, I'm going to have to apply one of the properties. And on this side, I have a minus sign, which means I'm going to probably use the quotient property, which says that if I have the difference of 2 logarithms of the same base, then I can rewrite that as the logarithm of x over x minus 4. Now again, me even doing that operation is working under the assumption that that I'm producing values that would exist when I take their natural logs. So for instance, the x minus 4, I know that x has to be greater than 0 for this one to work. X has to be greater than 4 for this to work. So to make the whole thing actually carry through, x has to be more than 4. If it's not more than 4, it would be extraneous. I need to throw it out. Now I do have a single logarithmic statement on the left, and I do have a single logarithmic statement on the right. So now these would cancel at this point. And so now I can rewrite the left-hand side as x over x minus 4 equaling 3. Now, if you remember from earlier in this course, this is now a rational equation. And I would usually at this point, if I was just presented with this equation, rational equations also have extraneous solutions themselves. So, I would usually have to say at this point, okay, what's any issues I could have with this? And I would probably say that, well, x can't be 4 because that's going to create something on the left-hand side that's not going to exist. But me already having the fact that this has to be greater than 4, I don't have to make that statement again. I mean, we're already working under the premise that x has to be more than 4 for any of this stuff to go on. So any answer I get that isn't over 4 would have to be thrown out if that should ever happen. So as I go through this now, thinking of this as 3 over 1, I do my cross multiplication. I'm going to have, and this is all in an effort to try to get x's out of the denominator. I'm going to have x equaling 3 times x minus 4, which is going to be x equaling 3x minus 12. Subtract 3x from both sides, I get a minus 2x over here, negative 12. Divide both sides by negative 2. I get that x equals 6. So this comes out to be a really nice answer. And if I just go in and now put that in, the natural log of 6 minus the natural log of 2 equals the natural log of 3. 2 ways I can check that. I mean, I can actually put the values into a calculator. This side here ends up, when I carry through that subtraction and everything, I'm going to have 1.098 approximately, which is what natural log 3 is. Or I could use the fact that, well, that's according to the quotient property again, that's going to be 6 over 2. And 6 over 2, of course, is 3. So I mean, so I don't need the calculator to check this one in particular because I could use the property to actually help me out with that one as well. And usually the answers that are integer and base is actually a little easier to handle with that. Moving on to the last one, part C. A little bit more problematic. I don't have any logarithmic statement on the right-hand side. So I just can't drop out logarithms, in any sort of way with this problem the way it is. I have stuff with logarithms on one side equaling a number. Now, if I had the log base 20 of just one quantity equaling 1, I could handle that. I could deal with that just fine. I guess rewrite this as an exponential equation and then go from there to solve it. I don't have that though. I need to have a single logarithmic statement on the left-hand side before I can take what I have and rewrite it as an exponential equation. So I need to figure out a way of doing that. Luckily, I have the properties that we learned about in the previous lesson. And those properties say, by the product property, since I have this addition here, I can rewrite this as the log base 20 of x minus 7 times x plus 5, and that would equal 1. So now I do have a single logarithmic statement. Now again, all this is working under the assumption that this exists. I mean, so I have here for this logarithm to exist, x has to be more than 7, because if it's 7 or less, I'm going to have 0 or negatives, and I can't do that. Here, x has to be greater than negative 5. So for any answer to be considered for this, it has to be more than 7. If I end up with anything that falls below that, it's not an answer. So with this now, I can rewrite this as foiling this out. I'm going to have x squared minus 2x minus 35 equaling 1. Again, I have a single logarithmic statement here. I could have done this in the previous step, or combined steps, but now I can rewrite this as an exponential. 20 to the first power equals x squared minus 2x minus 35. I can subtract 20 from both sides, and I like having my stuff on the left, so I'm going to have x squared minus 2x minus 55 equaling 0. This is now a quadratic equation. So, and what you find out is that there's not many factors of 55 that are integer factors, and none of them really give you a difference of -2 or give you an answer of -2. So, I'm going to use the quadratic formula because I do have it set equal to 0. And we have 2 plus or minus the square root of 4, which is what 2 squared is, minus 4 times 1 times a negative 55 all over 2 times 1. X is going to be 2 plus or minus the square root of 224 all over 2, which can be further simplified. I'm not writing an X up there. Further simplified into 2 plus or minus the square root of 16 times the square root of 14 all over 2, which gives me 2 plus or minus 4 square root 14, which means I'm going to have 1 plus or minus 2 square root of 14. So I do have two values here. X equals 1 plus 2 times the square root of 14, or x equals 1 minus 2 times the square root of 14. And these are the exact numbers. Now the thing is, I have to keep in mind now, okay, well, are any of these extraneous? I should make sure that they work, but are any of them extraneous? Luckily, most of the time with logarithmic equations, if they're able to be put into the logarithm and the logarithm can be done, it should work and it should be fine. If it can't, then that's extraneous. Okay. 1 plus 2 times the square root of 14 is a positive number, because 1's positive, 2 times the square root of 14 is a positive number. I'm great. Now the square root of 14 is somewhere between 3 and 4, closer to 4, like 3.7-ish. So if I do 1 minus 2 times 3.7-ish, I'm going to have a negative number. This is less than 0. If I have a number that's less than 0, I certainly cannot put it into the x minus 7, because I'm going to have a negative number being subtracted by 7, making it even more negative. So this one here is extraneous. making this the one and only answer. And if you do put it in, it does work. And that brings us to the end of this video. So if you have any additional questions, please make sure to bring them up in class or to see me during my office hours. Until I see you in one of those places or until the next video, I bid you a good day and I'll see you around.